Picture this: every atom in your body, every speck of dust on Earth, even the light from the farthest galaxies, all part of an endless cosmic dance that has been unfolding for nearly 14 billion years. The universe doesn't waste a single particle. Instead, it recycles, transforms, and reinvents itself on scales so vast they defy comprehension. Stars explode in brilliant supernova, scattering their remains across space, only for those very same elements to coalesce into new worlds, new suns, even new life. This isn't science fiction, it's the breathtaking reality of how the universe recycles itself, a process so grand it spans trillions of years and shapes the destiny of everything that exists. Think about the last time you threw something away: a piece of paper, a plastic bottle, maybe an old phone. On Earth, recycling is something we do to reduce waste. But out there, in the infinite expanse of space, recycling isn't just a choice, it's the law. From the moment the first stars ignited, the cosmos has been locked in an eternal loop of creation and destruction, where endings are merely new beginnings in disguise. When a massive star collapses, it doesn't just vanish. It seeds the galaxy with the building blocks for planets, for oceans, for living things. The iron in your blood, the calcium in your bones, they were forged in the hearts of dying stars billions of years ago. You are quite literally made of stardust, and so is everything around you. But the story doesn't end there. The universe's recycling program goes far beyond stars and planets. Galaxies themselves collide and merge, their gravitational dances reshaping the cosmic landscape. Dark energy, that mysterious force pushing the universe apart, may one day decide its ultimate fate. Will everything drift into cold, empty darkness, or could there be a rebirth waiting in the distant future? These aren't just abstract questions, they're clues to understanding where we came from, where we're headed, and our place in this unimaginably vast cycle. So let's embark on this journey together, tracing the steps of cosmic recycling from the smallest atoms to the largest structures in existence. By the end, you'll see the universe and your place in it in a whole new light. Stars are the ultimate cosmic alchemists, transforming the simplest elements into the ingredients for everything we know. Their story begins in vast, swirling clouds of gas and dust called nebulae, stellar nurseries where gravity slowly pulls matter together. Over millions of years, these clumps grow denser and hotter until nuclear fusion ignites in their cores and a star is born. A newborn star like our Sun spends most of its life in perfect balance, fusing hydrogen into helium and radiating light across the cosmos. But this stability doesn't last forever. As a star ages, it begins to change. For smaller stars, the end is quiet. They gradually shed their outer layers, leaving behind a glowing core called a white dwarf. But for massive stars, death is far more spectacular. When they exhaust their fuel, their cores collapse in a fraction of a second, triggering a cataclysmic explosion, a supernova. In that blinding flash, temperatures soar high enough to forge elements heavier than iron, from gold to uranium. The shockwave blasts these newly minted atoms into space, scattering them like cosmic seeds. These scattered remnants don't just vanish, they mix with interstellar gas, eventually becoming part of new nebulae, where gravity pulls them back together to form the next generation of stars and planets. Our solar system is proof of this endless cycle: the iron in Earth's core, the oxygen we breathe, even the silicon in your smartphone. All were forged inside ancient stars that died billions of years before the sun was born. Every time you look up at the night sky, you're seeing the aftermath of countless stellar lives and deaths, a cycle that has been repeating since the universe began. But stars aren't just recycling matter, they're also reshaping the cosmos itself. Supernova shockwaves trigger the birth of new stars by compressing nearby gas clouds, while stellar winds carve out vast bubbles in space. Even the humble white dwarf plays a role, its intense gravity pulling in surrounding material until it sometimes reignites in a runaway explosion called a nova. Every stellar death is a cosmic reset button, clearing the slate for the next act in the universe's grand story. And though our sun's eventual fate, a gentle puffing away of its outer layers, may seem less dramatic, even that quiet farewell will one day contribute to the birth of new worlds. Supernova are nature's most spectacular recycling plants, operating on a scale so immense it's hard to grasp. When a massive star reaches the end of its life, it doesn't fade quietly. It detonates with the energy of a billion suns, ripping itself apart in a blaze of light and fury. In that fleeting moment, temperatures soar to unimaginable heights, reaching billions of degrees. Under these extreme conditions, atoms are smashed together with such force that they fuse into entirely new elements far heavier than anything the star could produce during its lifetime. Gold, platinum, uranium, these rare and precious metals are born in the heart of a dying star's final, catastrophic breath. But the true magic happens after the explosion. The supernova's shockwave hurls these newly forged elements outward at nearly a tenth the speed of light, scattering them like cosmic confetti across interstellar space. This enriched material doesn't just float aimlessly, it mingles with vast clouds of gas and dust, becoming part of the raw ingredients for future star systems. Picture a celestial relay race where one generation of stars passes the baton of heavy elements to the next. Without supernova, the universe would be stuck with only the simplest atoms, hydrogen, helium, and a trace of lithium, leaving no material for rocky planets, no chemistry for life, no diversity at all. What's even more astonishing is how intimately connected we are to these violent cosmic events. Take a deep breath. The oxygen filling your lungs was once inside a star that exploded before our solar system existed. The gold in your jewelry, forged in a supernova's unimaginable heat. Even the device you're using to watch this video contains metals that were created in these stellar explosions. Every living thing on Earth is, in a very real sense, built from the ashes of long-dead stars. Supernova don't just recycle matter, they also shape the structure of galaxies. The shockwaves from these explosions compress nearby gas clouds, triggering the birth of new stars. In this way, a single supernova can set off a chain reaction of star formation, like a pebble starting an avalanche. Some astronomers even suspect that a nearby supernova may have played a role in the birth of our own sun, jump-starting the process that eventually led to planets and life. Yet for all their destructive power, supernova are ultimately creative forces. They're the universe's way of ensuring nothing goes to waste, that every atom gets a chance to be part of something new. From the ruins of a dying star, new worlds can form, new chemistry can emerge, and given enough time and the right conditions, new life can arise. This cosmic cycle of destruction and rebirth has been running for billions of years, and it will continue long after our sun has faded. The next time you look up at the night sky, remember those distant points of light aren't just stars. They're the furnaces where the building blocks of everything, including you, are being forged. When a massive star collapses, it doesn't just vanish. It leaves behind one of the universe's most extreme cosmic laboratories. If the remaining core is between 1 and 3 times the mass of our sun, it crushes down into a neutron star, an object so dense that a single teaspoon of its material would weigh as much as a mountain. Packed with more mass than our entire star, but squeezed into a sphere no wider than a city, neutron stars are the universe's ultimate pressure cookers, where matter is compressed beyond recognition. Atoms themselves collapse, protons and electrons merging into a sea of pure neutrons. Yet even in this bizarre state, these cosmic remnants play a vital recycling role. When two neutron stars spiral toward each other in a death spiral, their collision unleashes an explosion called a killanova, a fireworks display of cosmic proportions. In that violent merger, neutrons are flung outward at incredible speeds, rapidly assembling into heavy elements like gold, platinum, and uranium. A single neutron star collision can forge hundreds of Earth masses worth of precious metals in seconds, scattering them across galaxies. The gold in your wedding ring or the platinum in a catalytic converter likely originated in such a cataclysmic event billions of years ago. Black holes, the other possible endpoint for massive stars, take cosmic recycling to even greater extremes. These gravitational monsters warp space and time so severely that not even light can escape their grasp. But while they are famous for consuming everything in their path, black holes aren't just cosmic vacuum cleaners. As matter spirals into them, it doesn't vanish quietly. It puts on one last spectacular show. Friction heats the infalling material to millions of degrees, creating swirling disks of superheated plasma. Some of this material doesn't fall in at all. Instead, it gets funneled into narrow jets that blast outward at nearly the speed of light, stretching hundreds of thousands of light years into space. These jets are far from destructive, they're cosmic gardeners. When these high-energy beams slam into nearby clouds of gas, they compress the material, triggering waves of new star formation. Entire stellar nurseries can wake up because of a black hole's outburst. In this way, even the universe's most voracious eaters give back, turning destruction into creation on a galactic scale. Some astronomers believe the supermassive black holes at the centers of galaxies act like cosmic regulators, their outbursts preventing star formation from running wild while also seeding future generations of stars in distant regions. The dance between neutron stars and black holes reveals the universe's remarkable efficiency. Nothing is truly lost, only transformed. Elements forged in stellar cores get recycled through supernova. Neutron star mergers spread heavy metals across the cosmos, and black holes sculpt entire galaxies with their powerful outflows. Every ending plants the seeds for new beginnings. Long after our sun has faded and Earth is gone, these cosmic recyclers will continue their work, ensuring the universe never runs out of possibilities. Stellar nurseries are where the universe's grand recycling program begins its next chapter. These vast, glowing clouds of gas and dust nebulae are more than just beautiful cosmic landscapes. They're bustling factories where the remnants of long-dead stars are gathered, reshaped, and reborn. Every nebula is a testament to the universe's thriftiness, a place where nothing goes to waste. The raw materials floating in these cosmic clouds, hydrogen, helium, and heavier elements like carbon and oxygen, were once part of stars that lived and died billions of years ago. Now gravity steps in, pulling these scattered fragments together until they collapse under their own weight, heating up until nuclear fusion ignites. And just like that, a new star is born. Take the Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword. This stellar nursery, just 1,500 light-years away, is a perfect example of recycling on a cosmic scale. Inside its swirling depths, young stars blaze to life, surrounded by disks of gas and dust that may one day form planets. The nebula's vibrant glow comes from the intense radiation of these newborn stars, energizing the surrounding gas like a celestial neon sign. But what's truly remarkable is that the very material giving birth to these stars was once part of earlier generations' stars that exploded or gently shed their outer layers, returning their substance to the cosmos. This cycle isn't just happening in Orion. Across the universe, nebulae serve as cosmic cradles, ensuring that the heavy elements forged in stellar furnaces don't go to waste. Without them, there would be no rocky planets, no water, no chemistry complex enough for life. Every atom of oxygen in Earth's atmosphere, every speck of silicon in its crust, was once part of a nebula like this, patiently waiting its turn to be woven into something new. Yet nebulae aren't just passive repositories of stellar debris. They're dynamic, ever-changing environments. Stellar winds from newborn stars carve out cavities in the gas, while shock waves from nearby supernova compress the material, triggering even more star formation. It's a self-sustaining process, one generation of stars paving the way for the next. And as these young stars mature, some will eventually return their enriched material to the interstellar medium, ready to be recycled once again. The beauty of this system lies in its simplicity and efficiency. The universe doesn't hoard its resources or let them sit idle. Instead, it constantly repurposes them, turning the ashes of old stars into the building blocks of new ones. From the tiniest dust grain to the largest gas cloud, every bit of matter has a role to play in this endless cycle of creation and renewal. So the next time you gaze up at a nebula, remember, you're not just looking at a pretty cloud of gas. You're witnessing the universe's workshop where the raw materials of existence are endlessly remade. Galactic collisions might sound like cosmic disasters, but they're actually the universe's way of hitting the refresh button. When two galaxies meet, it's not a simple crash, it's an intricate gravitational dance that can last billions of years. Picture two swirling crowds of stars, gas, and dark matter, each with their own rhythm, slowly intertwining until they become something entirely new. The sheer scale is mind-bending. Our Milky Way contains over 100 billion stars, and when it eventually collides with the Andromeda galaxy, the resulting merger will involve twice that number. Yet in this vast chaos, there's extraordinary order. What makes these collisions so remarkable isn't just their spectacle, it's what they leave behind. As galaxies merge, their gas clouds slam together, compressing under immense pressure. This triggers explosive waves of star formation, like cosmic fireworks lighting up the darkness. Suddenly, stellar nurseries ignite across the merging galaxies, giving birth to millions of new suns in just a few million years, a blink of an eye in cosmic terms. Some of these newborn stars will be surrounded by fresh planets, creating entirely new worlds from the recycled material of two once separate galaxies. But the real magic happens in the aftermath. As the galaxies complete their merger, they don't just mix, they transform. The familiar spiral arms of galaxies like ours get stretched and twisted into new shapes, often forming an elliptical galaxy with a smooth, glowing core. The stars themselves rarely collide. Space is too vast, but their orbits get completely rewritten by the shifting gravitational forces. It's like watching two schools of fish merge into one, with every individual finding a new path through the waters. Our own Milky Way is no stranger to this process. Astronomers have found stellar streams, long ribbons of stars, that are the remnants of smaller galaxies our galaxy has already absorbed. These cosmic fossils tell the story of our galaxy's growth through mergers, a process that will continue until the Milky Way and Andromeda become one. The resulting galaxy, sometimes nicknamed Milkomda or Milkdromda, will be a luminous hybrid bearing the legacy of both its parents. Perhaps most astonishing is how these collisions redistribute the building blocks of the universe. The violent interactions fling gas and stars far beyond their original galaxies, seeding intergalactic space with material that might one day form new dwarf galaxies. Even planets orphaned from their stars during the merger might drift through the darkness, carrying the potential for life into the void. Far from being destructive, galactic collisions are the universe's way of stirring the pot, ensuring no resource goes unused in the grand scheme of cosmic evolution. This relentless recycling extends beyond just matter. The supermassive black holes at the centers of merging galaxies spiral toward each other, eventually merging in an event so powerful it sends ripples through space-time itself. These gravitational waves, first detected in 2015, are the universe's way of broadcasting its most dramatic renovation projects across the cosmos. The energy released during such mergers can heat surrounding gas to millions of degrees, temporarily shutting down star formation, only for it to reignite later as the galaxy settles into its new form. What seems like an ending is really a transformation. Just as forests need occasional wildfires to renew themselves, galaxies need these collisions to stay vibrant and evolving. The universe doesn't let anything go to waste, not stars, not gas, not even the gravitational energy of merging black holes. Everything gets repurposed, reshaped, and given new meaning in this never-ending cycle of destruction and creation. So when you look up at Andromeda, that faint smudge of light in the night sky, remember you're gazing at our galaxy's future dance partner, and the next great chapter in the story of cosmic recycling. Dark matter is the universe's invisible scaffolding, a ghostly presence whose gravity shapes everything we see, yet we've never directly observed it. Think of it like the wind. You can't see it, but you feel its effects everywhere. Without dark matter's gravitational pull, galaxies wouldn't spin the way they do, clusters wouldn't hold together, and the cosmic recycling program we've been exploring would grind to a halt. It's the silent architect behind the scenes, weaving order into the chaos of the universe. Here's how it works. When we measure the mass of galaxies based on visible stars and gas alone, the numbers don't add up. Stars at the edges of spiral galaxies, like our Milky Way, move far too quickly for the gravity of visible matter to hold them in orbit, the only explanation. An enormous halo of unseen matter, dark matter, wrapping around each galaxy like an invisible glove, its gravity keeping everything from flying apart. This hidden mass doesn't just anchor galaxies, it guides them. When galaxies collide, it's dark matter that orchestrates the dance, its gravitational field shaping how gas clouds merge and stars realign. But dark matter's role goes beyond just holding galaxies together. It's also the universe's ultimate recycler, ensuring no speck of matter gets left behind. After a supernova explodes, ejecting heavy elements into space, dark matter's gravity helps corral those scattered atoms back into dense regions where new stars can form. Without it, enriched gas might drift endlessly through the void, never coalescing into new solar systems. Even the vast cosmic web, the filamentary structure connecting galaxy clusters, owes its existence to dark matter's gravitational pull, creating highways along which matter flows and gathers. The most fascinating part, dark matter doesn't just preserve structure, it accelerates creation. In the early universe, slight density fluctuations in dark matter acted like seeds, pulling ordinary matter into clumps that eventually grew into galaxies. Today, it continues to shape the birth of stars by compressing gas clouds in its gravitational grip. Some astronomers even suspect dark matter's influence might explain why certain galaxies produce stars at explosive rates, as if something unseen is squeezing the cosmic fuel supply. Yet for all its importance, dark matter remains one of the greatest mysteries in science. It doesn't emit, absorb, or reflect light. It interacts with ordinary matter only through gravity. We know it's there because of the way galaxies move, the way light bends around galaxy clusters, even the way the universe expanded after the Big Bang. But what it's made of, that's still an open question. Candidates range from hypothetical particles called WIMP, weakly interacting massive particles, to primordial black holes formed in the universe's first moments. What's clear is that without dark matter, the universe as we know it wouldn't exist. No spiral galaxies, no stellar nurseries, no planets, just a diffuse sea of gas and dust, never organizing into the rich tapestry we see today. Every time a star recycles its material into a new generation, dark matter's invisible hand is there, guiding the process. So while we may never see it directly, its fingerprints are everywhere in the spin of galaxies, the glow of distant clusters, even the very fact that we're here to ponder its existence. The next time you look up at the night sky, remember, what you're seeing is only half the story. The rest is written in the language of gravity, by an unseen force that keeps the cosmic wheels turning. If dark matter is the universe's invisible scaffolding, dark energy is its mysterious engine, an unseen force working in the opposite direction, pushing everything apart at an accelerating pace. Discovered in the late 1990s when astronomers observed distant supernova glowing dimmer than expected, dark energy revealed a shocking truth. Instead of slowing down after the Big Bang, the universe's expansion is speeding up. This wasn't just unexpected, it overturned decades of cosmic understanding. Imagine throwing a ball into the air, only to watch it shoot faster into the sky instead of falling back down. That's the baffling reality we're grappling with on a cosmic scale. What makes dark energy so puzzling is that it seems to be woven into the fabric of space itself. Unlike matter or radiation, its density doesn't dilute as the universe expands. More space means more dark energy, creating a runaway effect where the expansion accelerates over time. Some theories suggest it could be a property of empty space, what Einstein once called the cosmological constant, while others propose it's an entirely new kind of field or energy. What's certain is that this force now dominates the universe's evolution, accounting for nearly 70% of its total energy content. The big question is what this means for cosmic recycling. On one hand, dark energy's relentless push could spell a cold, lonely future. As space stretches faster, distant galaxies will fade from view, their light stretched beyond detectability. Eventually, even nearby galaxy clusters may be ripped apart, leaving islands of stars isolated in an ever-darkening void. This scenario, called the Big Freeze, suggests a universe where recycling grinds to a halt. No new collisions, no fresh star formation, just fading embers of heat and light. But there's another, more tantalizing possibility. Some theories suggest dark energy might not be constant. It could evolve over time, perhaps even reversing its effects. In this scenario, the accelerated expansion could someday slow, stop, or even flip into contraction. Picture the universe taking a deep breath before exhaling, collapsing back toward a singularity in a mirror image of the Big Bang, a big crunch. If that happens, all the scattered matter and energy could be recycled anew, compressed and reheated until the universe reboots itself in another fiery genesis. Even more speculative are models where dark energy interacts with matter in unexpected ways. Could it somehow catalyze new forms of particle creation in the far future? Might it warp the vacuum of space so profoundly that new quantum fluctuations birth entirely fresh universes? While these ideas venture into theoretical territory, they highlight a profound truth. Dark energy isn't just a destroyer. It's a wild card that could reshape the universe's recycling mechanisms in ways we're only beginning to imagine. For now, dark energy remains one of cosmology's greatest puzzles. Every observation from the distribution of galaxy clusters to the cosmic microwave background hints at its influence, yet its true nature eludes us. What we do know is that this mysterious force is writing the next chapter of the universe's story, one where the fate of every atom, every star, and every galaxy hangs in the balance. Whether it leads to eternal expansion, cosmic rebirth, or something stranger still, dark energy ensures that the universe's recycling program is far from predictable, and that the final act of this grand cosmic drama has yet to unfold. Our galaxy, the Milky Way, isn't just a bystander in this cosmic recycling process, it's an active participant, a swirling metropolis of stars where birth and death play out on scales both grand and intimate. Right now, somewhere in its spiral arms, a massive star is breathing its last in a supernova explosion, while in the Orion arm, new stars flicker to life inside glowing nebulae. This cycle has been repeating for over 13 billion years, with generations of stars leaving their mark before passing the torch to the next. But the Milky Way story doesn't end there. Like all galaxies, it's destined for a dramatic transformation, one that will rewrite its structure and scatter its stars into a new cosmic chapter. The biggest event in our galaxy's future isn't just another supernova or the quiet fading of the sun. It's a collision of titans, the Milky Way, and its nearest neighbor, the Andromeda galaxy, currently racing toward each other at nearly 250,000 miles per hour. In about 5 billion years, these two spiral galaxies will begin a gravitational tango that lasts for eons. At first, the encounter will look more like a slow-motion rearrangement than a crash. Stars are so far apart that most will glide past one another untouched, their paths bent by gravity like dancers weaving through an elaborate routine. But the gas and dust between them, that's where the real action happens. As the galaxies draw closer, their interstellar clouds will slam together, compressing under immense pressure and igniting a fireworks display of star formation. Imagine whole constellations blazing to life at once, their light outshining the combined glow of both galaxies' cores. For a brief cosmic moment, the merged galaxies will become a stellar nursery on a scale unseen since the early universe. But this frenzy won't last. Eventually, the chaotic orbits of stars will settle. The gas will either form stars or be blown away by stellar winds, and what remains will be something entirely new, a smooth, featureless elliptical galaxy, its stars orbiting in random directions like a swarm of bees. What happens to our solar system in all this? Surprisingly, it might survive the merger relatively unscathed. The Sun, by then a fading white dwarf, and any remaining planets will likely be flung to the galaxy's outer reaches, far from the crowded core. Earth, if it still exists, would witness a night sky transformed no familiar Milky Way band, but instead a dazzling scatter of stars against a backdrop of merging galactic cores glowing with the light of countless suns. Andromeda's central black hole and our own Sagittarius, a star, will spiral together, eventually merging in a gravitational wave event that shakes the fabric of space-time itself. This isn't just a distant spectacle, it's a reminder that the universe operates on timescales beyond human comprehension. Every atom in our bodies, every mountain on Earth, even the light from our sun, is part of a cycle that began long before us and will continue long after. The Milky Way's fate mirrors that of all galaxies, to grow, to merge, and to eventually fade as dark energy stretches the universe ever further apart. Yet even in that distant future, the materials of our solar system, the carbon in our cells, the iron in our blood will persist, adrift in a reshaped galaxy, or perhaps blown into intergalactic space, waiting for their next role in the universe's unending story of renewal. Far from being a cosmic tragedy, the Milky Way's merger with Andromeda is just another turn of the wheel. Galaxies have been colliding since the first structures formed, and each collision seeds the universe with fresh generations of stars and planets. The elements forged in our galaxy's stars, the oxygen we breathe, the calcium in our bones, will one day be part of new worlds, new atmospheres, maybe even new life. Nothing is truly lost in the universe. It's all just waiting to begin again. Planetary nebulae are the universe's way of turning stellar goodbyes into breathtaking new beginnings. When a star like our Sun reaches the end of its life, it doesn't go out with a bang like its massive cousins. Instead, it bows out gracefully, shedding its outer layers in a slow, luminous exhale. These expelled layers don't just vanish into the void. They form intricate, glowing shells of gas and dust that shimmer across thousands of light years, painting the cosmos with their ethereal beauty. What we're seeing is more than just a farewell. It's the star's final gift to the universe, a payload of enriched material ready to be recycled into future generations of stars and planets. Take the Cat's Eye Nebula, one of the most complex and mesmerizing planetary nebulae ever observed. Its intricate layers and radiant filaments look like a celestial work of art, but every swirl and ripple tells a scientific story. At its heart lies a hot, dense core, the dying star's exposed remains, now a white dwarf. As this stellar ember radiates intense ultraviolet light, it energizes the surrounding gas, making it glow in vivid hues of blue, green, and red. The nebula's intricate structures, delicate loops, sharp spikes, and concentric shells reveal the star's turbulent final acts, as if it coughed out its material in rhythmic pulses over thousands of years. But the real magic happens long after the light show fades. Over hundreds of thousands of years, the nebula's glowing gases will disperse, mixing with the interstellar medium like cream swirling into coffee. These atoms, carbon, nitrogen, oxygen, were forged in the star's core during its lifetime, and now they're returning to space, carrying the seeds of future chemistry. When this enriched material eventually collapses into new molecular clouds, it won't just form generic stars, it'll create solar systems with rocky planets, organic molecules, and all the ingredients needed for life. The iron in your blood, the oxygen in your lungs, even the calcium in your bones, much of it passed through a planetary nebula like this one before finding its way to Earth. What's astonishing is how efficient this process is. A single sun-like star might lose 40 to 60% of its mass as it becomes a planetary nebula, scattering enough heavy elements to seed countless new worlds. And because stars like ours are so common, making up nearly 90% of all stars in the Milky Way, their gentle deaths play an outsized role in cosmic recycling. While supernovae grab headlines for their explosive drama, planetary nebulae are the quiet, steady workforce of galactic renewal, ensuring no atom goes to waste. The next time you gaze at images of these cosmic butterflies, the Helix Nebula with its eerie eye, the Ring Nebula's perfect smoke circle, or the Butterfly Nebula's delicate wings, remember you're witnessing a celestial passing of the torch. Every delicate filament and glowing shell is a testament to the universe's endless creativity, where even death is just another step in the cycle of rebirth. Long after the last glow fades, the legacy of these stars lives on in new suns, new planets, and perhaps one day, in new life, looking up at the skies and wondering about its own origins. White dwarfs are the universe's quiet custodians of cosmic memory, glowing remnants of stars that once shone like our sun. When a star of similar mass exhausts its nuclear fuel, it doesn't explode, it undergoes a more graceful transformation. The outer layers drift away as a planetary nebula, while the core collapses into an object no larger than Earth but containing nearly half the original star's mass. Imagine compressing all the material in 1,000,000 Earths into something the size of our planet. That's the incredible density of a white dwarf, where a single sugar cube's worth of matter would weigh several tons. For billions of years, these stellar embers radiate the last of their heat into space, glowing faintly like dying coals in a cosmic fireplace. Their light isn't dramatic, it's the soft blue-white glow of intensely hot but fading energy. What makes them remarkable isn't their brightness but their endurance. A white dwarf's cooling process is achingly slow, taking trillions of years, far longer than the current age of the universe. Some of the first white dwarfs ever formed are still out there, only slightly dimmer than when they were born. Yet even in their twilight, white dwarfs play a crucial role in cosmic recycling. Their intense gravity acts like a celestial filter, separating elements by weight. Heavier elements like oxygen and carbon sink to the core, while lighter ones float to the surface in distinct layers, an onion-like structure preserved for eons. When white dwarfs occasionally pull material from companion stars, this layered chemistry can trigger runaway nuclear reactions, creating brilliant novas that briefly outshine entire galaxies. These explosions don't destroy the white dwarf, they simply add another chapter to its life, scattering fresh elements into space while the dense core remains intact. The ultimate fate of white dwarfs depends on the universe itself. In the far future, when all stars have burned out and galaxies have drifted apart, white dwarfs will be among the last visible objects in the cosmos. Eventually, they'll cool to black dwarfs called dark spheres of crystallized carbon and oxygen. But even then, their material won't be lost. Quantum mechanics suggests that over unimaginable timescales, these stellar remnants could slowly evaporate through Hawking radiation, their atoms returning to the universe's raw material pool. What's truly humbling is realizing our sun's destiny lies in this quiet fade. 5 billion years from now, after swelling into a red giant and shedding its outer layers, it too will become a white dwarf, a dense, Earth-sized cinder drifting through the Milky Way's ruins. The planets may be gone, scattered or vaporized during the red giant phase, but the sun's core will persist, a silent monument to the star that once warmed our world. Every white dwarf we see today is a glimpse of our solar system's distant future, a reminder that even stars have life cycles, and that endings in the universe are often just transitions in disguise. These stellar ghosts teach us an important cosmic lesson. Not all recycling happens through violent explosions or dramatic collisions. Sometimes, the most profound transformations occur in the quiet glow of fading embers, as the universe patiently repurposes its materials across timescales beyond human imagination. The next time you look up at the night sky, consider that some of those faint points of light might be white dwarfs, the gentle caretakers of the cosmos, preserving star stuff until the universe is ready to use it again. Black dwarfs are the universe's final resting place for stars like our sun, cold, dark husks drifting through an ever-expanding cosmos. After white dwarfs exhaust their remaining heat over trillions of years, they don't vanish. Instead, they transition into these invisible relics, their glow faded but their gravitational pull still shaping the fabric of space around them. Picture a celestial graveyard where the tombstones are made of crystallized carbon and oxygen, each one heavier than a planet yet darker than the void between galaxies. These aren't just dead stars, they're frozen time capsules, preserving the elements of ancient suns long after their light has gone out. What's fascinating about black dwarfs isn't just what they are, but when they'll exist. The universe is currently only 13.8 billion years old, far too young for even the first white dwarfs to have cooled into this final state. The process takes so long that no black dwarfs likely exist yet. We're talking about a timescale that dwarfs the age of the cosmos itself, a future so distant that all the stars we see today will have burned out and galaxies will have drifted apart beyond recognition. Yet this inevitable cooling is a reminder that even the most stable objects in the universe aren't permanent. Given enough time, everything changes. Despite their invisibility, black dwarfs still play a role in the cosmic recycling program. Their mass, though locked away, continues to interact gravitationally with other objects. In a far future galaxy populated by black dwarfs, neutron stars, and black holes, these dark remnants could still bend light, influence the motion of nearby objects, or even merge in slow-motion collisions over eons. Some theories suggest that black dwarfs might eventually trigger one last act of recycling. If two collide under just the right conditions, their combined mass could reignite nuclear fusion in a final, fleeting burst of light. The existence of black dwarfs also raises profound questions about the universe's ultimate fate. In a cosmos dominated by dark energy, where space stretches faster and faster, these stellar ghosts might one day be all that remains of entire galaxies. As the universe expands, even black dwarfs could eventually be torn apart by the accelerating fabric of spacetime itself, their atoms scattered into the void. Or, in a more cyclical universe, their material might someday collapse back into a singularity, reborn in a new Big Bang. Either way, their story reminds us that even in the coldest, darkest corners of existence, nothing is truly lost, only transformed. There's a quiet poetry to black dwarfs. They represent the end of stellar evolution, yes, but also the persistence of matter across incomprehensible timescales. Every carbon atom in a black dwarf was once part of a shining star, a planet, or perhaps even a living world. Now, locked in cosmic deep freeze, those atoms wait patiently, silently, for whatever comes next. The universe doesn't do endings, only transitions. And while black dwarfs may mark the final chapter for stars like our Sun, they're also a testament to the unyielding creativity of the cosmos, where every ending is just a prelude to something new. The universe's grand recycling program has been running for nearly 14 billion years, but nothing lasts forever, not even the cosmos itself. Scientists have long grappled with two competing visions for how it all might end, each with dramatic implications for the future of matter, energy, and the possibility of rebirth. The first scenario, known as the Big Crunch, plays out like a cosmic rewind button. If gravity eventually overcomes dark energy's outward push, the expansion of the universe could slow, halt, and reverse. Galaxies would begin rushing toward one another, their collisions triggering violent bursts of star formation as gas clouds compress. Temperatures would rise across the cosmos as space itself contracts, until eventually, everything, every planet, every black hole, every stray atom collapses into a single point of infinite density. It would be a mirror image of the Big Bang, a fiery finale where the universe essentially reboots itself. In this scenario, the ultimate form of recycling isn't just stars or galaxies, it's reality itself, collapsing and birthing a new cosmos from the ashes of the old. But there's another, colder possibility. If dark energy's acceleration continues unchecked, we might face the Big Freeze, a slow, silent fading of all things. As space stretches faster, galaxies beyond our local group would vanish over the cosmic horizon, their light stretched beyond detectability. Star formation would gradually cease as gas clouds grow too diffused to collapse. Even black holes, the last bastions of structure, would eventually evaporate via Hawking radiation over incomprehensible timescales. The universe would approach absolute zero, a state of maximum entropy where no energy can be extracted, no work can be done, and no new structures can form. It sounds like a definitive end, but here's the twist. Quantum physics suggests that even in this frozen void, tiny fluctuations in the vacuum could spark new Big Bangs. Like bubbles forming in an infinite sea, these quantum events might birth entirely new universes with their own laws of physics. The Big Freeze, then, isn't necessarily the death of everything. It could be the incubator for realities we can't yet imagine. The choice between these two fates hinges on a cosmic tug of war between gravity and dark energy, a battle we're only beginning to understand. Current observations favor the Big Freeze scenario, with dark energy's influence seemingly growing stronger over time. Yet the universe has surprised us before. Dark energy's properties could change, or new physics could emerge that alters the trajectory entirely. Some theories even propose a cyclical universe, where expansion and contraction repeat in an endless loop, a cosmic heartbeat spanning trillions of years. What's remarkable is how both scenarios, despite their stark differences, preserve the universe's knack for reinvention. Whether through a fiery collapse or quantum rebirth, the materials of our reality, the atoms in our bodies, the light from distant quasars, even space-time itself, might one day be part of something entirely new. The universe doesn't seem to believe in true endings, only transformations. So while we may never witness these distant epochs ourselves, we can take comfort in knowing that the cosmic story doesn't end with us. It simply turns the page. The idea that our universe might be just one bubble in an endless cosmic froth is both exhilarating and humbling. According to cosmic inflation theory, the rapid expansion that jump-started our universe could still be happening elsewhere, spawning new universes like bubbles forming in a boiling pot. Each of these bubble universes might have its own unique physics, different constants, different forces, even different numbers of dimensions. In this multiverse scenario, the concept of recycling takes on a staggering new dimension. Instead of matter being reused within a single universe, entire universes could emerge from the collapse or collision of others, like cosmic phoenixes rising from the ashes of their predecessors. Imagine a scenario where two universes collide in the higher dimensional bulk of the multiverse. The energy released could trigger the birth of entirely new universes, each carrying fragments of their parent universe's physical laws. Or consider vacuum decay, where a quantum fluctuation in one universe creates a bubble of lower energy vacuum that expands at light speed, rewriting the laws of physics as it goes. This catastrophic event in one universe might simultaneously create the conditions for new universes to form elsewhere in the multiverse fabric. The destruction of one reality becomes the genesis of another in an endless cycle of creation and transformation. Some versions of string theory take this even further, suggesting that our three-dimensional universe might be a membrane, or brane, floating in a higher dimensional space. When these branes collide, the resulting energy could spark new Big Bangs, effectively recycling space-time itself. The ekpyrotic universe model proposes exactly this, painting a picture where our cosmic history isn't a single linear timeline but part of an eternal cycle of brane collisions. Each collision resets the cosmic clock, scattering matter and energy that eventually coalesce into galaxies, stars, and planets, only to be scattered again in the next collision. What makes these theories so compelling is how they transform our understanding of cosmic recycling. No longer confined to stars and galaxies, the process now operates on the grandest possible scale. Black holes in one universe might seed the birth of another through their singularities. Dark energy's acceleration could stretch space so thin that quantum tunneling creates new universes in the voids between galaxies. Even the heat death of our universe, the eventual fading of all energy into useless warmth, might not be the end, but a pause before quantum fluctuations spark new inflationary periods elsewhere. The implications are staggering. If true, every atom in our bodies, every star in the sky, might have cycled through countless universes before arriving in ours. The carbon in your DNA, the iron in your blood, could be multiversal veterans with histories stretching back further than time itself. And when our universe grows cold and dark, its material might one day find new life in realities we can't even imagine. The cosmic recycling bin isn't just galaxy-sized, it's infinite. Yet for all their grandeur, these ideas remain speculative, pushing the boundaries of both physics and philosophy. They challenge us to rethink not just where matter comes from, but where reality itself originates, whether through colliding brains, quantum bubbles, or some mechanism we haven't yet conceived. The multiverse hypothesis suggests that recycling isn't just a feature of our universe. It might be the fundamental process that sustains existence itself. So the next time you gaze at the night sky, remember, those stars might be more than just distant suns. They could be threads in a tapestry woven across countless universes, each one part of a cycle without beginning or end. At the smallest scales imaginable, where particles flicker in and out of existence in fractions of a second, the universe might be hiding its most astonishing trick, the ability to birth entirely new realities from nothingness. Quantum fluctuations, those tiny, unpredictable changes in energy that occur even in perfect vacuum, aren't just mathematical curiosities. They could be the cosmic seeds for universes beyond our own, proof that recycling isn't limited to stars and galaxies, but extends to the very fabric of reality itself. Picture the vacuum of space not as an empty void, but as a bubbling cauldron of activity. At scales trillions of times smaller than an atom, particles and antiparticles constantly pop into existence, borrowing energy from nowhere before vanishing again. Most of these fluctuations last only moments, their energy quickly repaid to the universe, but under the right conditions, perhaps in the extreme gravity near a black hole's singularity, or in the unfathomable energies of the early cosmos, one of these fluctuations could grow. Instead of disappearing, it might inflate exponentially, stretching spacetime itself until it becomes a self-contained universe with its own physics, its own stars, its own possibilities. This isn't just speculation. The same quantum processes that govern particles on Earth might also shape the fate of the cosmos. Inflationary theory suggests our own universe began with a quantum fluctuation, a tiny bubble of false vacuum that expanded faster than light, creating the vast expanse we see today. If it happened once, why couldn't it happen again? Some models propose that black holes could be portals to new universes, their singularities birthing baby universes where the laws of physics differ slightly from our own. Every collapsing star, every galactic collision might be sowing the seeds for realities we'll never see. The implications are staggering. If true, our universe might be just one leaf on an infinite tree of branching realities, each with its own history, its own forms of matter, even its own versions of life. The atoms in your body might one day find themselves recycled not just into new stars, but into entirely new dimensions of existence. And when our cosmos reaches its final state, whether a heat death or a big crunch, quantum fluctuations could ensure the story doesn't end. Like cosmic phoenixes, new universes might rise from the ashes of the old, each carrying fragments of what came before while writing entirely new chapters. What's truly remarkable is how this idea turns our understanding of recycling upside down. We're used to thinking of it as a process for matter, stars turning hydrogen into helium, supernova scattering iron across space. But if quantum fluctuations can spawn universes, then the universe isn't just recycling materials, it's recycling existence itself. Every moment, somewhere in the infinite reaches of spacetime, a new reality might be flickering to life, its physics subtly different, its future unwritten. Some could collapse instantly, while others might grow to rival our own in scale and complexity. This vision of the cosmos is both humbling and exhilarating. It suggests that even in the coldest, darkest corners of space, even in what we call nothingness, the potential for creation never truly vanishes. The universe doesn't just reuse what already exists, it endlessly reinvents the rules of the game, ensuring that no two realities are ever quite the same. So the next time you hear about quantum physics being strange or counterintuitive, remember, it might not just be describing how particles behave. It could be revealing the universe's deepest secret, that endings are illusions, and every fade to black is just the prelude to a new beginning. Time and entropy are locked in an eternal cosmic tug of war, one slowly unraveling the universe while the other fights to rebuild it. Entropy, the measure of disorder, dictates that everything naturally trends toward chaos over time. Your coffee cools, stars burn out, even mountains crumble to dust. Yet against this relentless march stands something extraordinary, the universe's recycling mechanisms. Every time a nebula collapses into a star, or a supernova scatters heavy elements across space, pockets of order emerge from the chaos like islands in a rising tide. Stars are entropy's greatest adversaries, taking diffuse clouds of gas and sculpting them into precise, glowing spheres with clear structure and predictable rhythms. For billions of years, gravity acts as the universe's counterbalance to decay, pulling scattered matter together to forge new cosmic architectures. But this struggle isn't eternal. Even stars are temporary victories against entropy's dominance. Consider our own sun. It spends its life converting simple hydrogen into more complex helium, creating localized order through nuclear fusion. Yet the energy it radiates into space increases the universe's overall entropy far more than the sun's internal organization reduces it. This paradox lies at the heart of cosmic recycling. Every act of creation disperses energy in ways that ultimately contribute to the universe's disorder. Galaxies, those glittering cities of stars, face the same dilemma. Their spiral arms and clustered stars appear meticulously arranged, but their collisions and mergers release torrents of heat and light energy that forever escapes into the void, never to be recaptured. The irony is profound. The very processes that sustain cosmic recycling, supernova enriching galaxies with heavy elements, black holes merging and releasing gravitational waves, even planets forming from debris disks, all accelerate entropy in the grand scheme. Each cycle leaves the universe slightly more disordered than before, like a baker kneading dough but losing flour with every fold. Given enough time, even the mightiest recycling engines will sputter. Star formation will slow as galaxies exhaust their gas, black holes will evaporate via Hawking radiation, and the universe will drift toward a state of maximum entropy, a featureless expanse where no energy can be harnessed for work, no structures can form, and no new stories can unfold. Yet here's the twist: entropy might not have the final word. Quantum mechanics hints that even in a lifeless, heat-dead universe, random fluctuations could spawn new pockets of order given enough time. Imagine a universe so vast and ancient that even the tiniest probability becomes inevitable, a region where atoms spontaneously align into complexity purely by chance, sparking a new cycle of creation. Some theories even suggest that dark energy's mysterious influence could one day wane, allowing gravity to reassert itself and pull the cosmos back toward rebirth. Whether through quantum resurrection or cosmic bounce, the universe may have tricks we've yet to imagine. For now, we witness the golden age of cosmic recycling, a fleeting epoch where stars still shine, galaxies still collide, and the universe teems with structure. The iron in our blood, the silicon in our planet's crust, even the light from distant quasars all testify to entropy's temporary setbacks. Though the battle is ultimately unwinnable, the fact that it's been raging for billions of years is nothing short of miraculous. Every atom forged in a dying star, every planet shaped by gravitational forces, represents a defiant whisper against the universe's slow fade, proof that even in a cosmos destined for cold stillness, the urge to create, to rebuild, and to endure is written into the fabric of reality itself. Black holes, those cosmic vacuum cleaners that swallow everything in their path, might seem like the ultimate dead ends in the universe's recycling program. But thanks to a revolutionary idea by physicist Stephen Hawking, we now know they're not eternal prisons, they're more like slow-release fertilizer for the cosmos. Hawking radiation, the faint glow of particles escaping a black hole's clutches, reveals an astonishing truth. Even these gravitational monsters eventually give back what they've taken. Picture a black hole not as a bottomless pit, but as a leaky bucket slowly dripping particles back into space over timescales so vast they dwarf the current age of the universe. Here's how it works. Quantum mechanics tells us that empty space isn't truly empty. It's a seething froth of virtual particles that constantly pop into existence in particle-antiparticle pairs, only to annihilate each other almost immediately. Near a black hole's event horizon, something extraordinary happens. One particle falls in while the other escapes, stealing a tiny bit of the black hole's energy in the process. To an outside observer, it looks like the black hole is emitting radiation, a faint whisper of heat against the cosmic background. Over unimaginable eons, this slow bleed causes the black hole to lose mass and shrink until, in a final burst of energy, it vanishes completely. What makes this process so remarkable isn't just the physics, it's what happens to all that trapped material. Every atom, every photon, every shred of information that fell into the black hole gets converted into Hawking radiation over time. The black hole's contents aren't destroyed, they're transformed, released back into the universe as raw energy that can eventually coalesce into new particles. In the far future, when all stars have burned out and galaxies have drifted apart, black hole evaporation might be the last cosmic recycling plant still in operation, converting gravitational prisons into the seeds of new possibilities. The implications are staggering. A stellar mass black hole might take 10 to the 67 years to evaporate. That's a 1 followed by 67 zeros. But supermassive black holes, the giants lurking at galactic centers, they could persist for 10 to the 100 years or more. Yet even these titans will eventually succumb, their final moments potentially releasing bursts of high-energy particles that could kickstart new chemistry in an otherwise dormant cosmos. Some theories even suggest that the particles emitted via Hawking radiation might carry subtle imprints of what fell in not as intact information, but as reshaped quantum states that subtly influence how new structures form. This slow-motion evaporation turns black holes into cosmic time capsules, holding onto matter and energy until the universe is ready to reuse them. In a sense, they're the ultimate conservators, locking away resources during chaotic eras of galactic collisions and supernova, only to release them when conditions are calmer and more stable. By the time the last black holes evaporate, the universe will be unimaginably old and cold, but those final particles could become the building blocks for whatever comes next, whether quantum fluctuations spark new universes or dark energy reshapes reality itself. Far from being endpoints, black holes emerge as patient participants in the universe's grand cycle, proving once again that nothing is truly lost, only held in reserve. Their evaporation reminds us that even the darkest corners of existence have a role to play in the endless dance of creation and renewal. So the next time you picture a black hole, don't just see a voracious predator, see a cosmic librarian, temporarily shelving the universe's raw materials until they're needed for the next chapter. The heat death of the universe paints a chilling portrait of the far future, a cosmos so stretched thin by expansion that all energy is evenly dispersed. No stars twinkle in the void, and even black holes have evaporated into faint whispers of radiation. In this bleak scenario, the universe reaches maximum entropy, a state where no temperature differences exist to power engines, no structures can form, and every process grinds to an eternal halt. It's the ultimate thermodynamic dead end, where time itself becomes meaningless because nothing changes anymore. Yet against this grim forecast, a daring question lingers. Could even this frozen wasteland hold the seeds of cosmic rebirth? Some theories suggest that the universe might have an escape clause written into the fabric of reality itself. Quantum fluctuations, those tiny bursts of energy that spontaneously occur in empty space, could, given enough time, trigger a staggering reversal. Picture a universe quadrillions of years older than today, where random quantum tunneling in the vacuum generates a microscopic bubble of false vacuum. If conditions are just right, this bubble could inflate exponentially, birthing an entirely new universe with its own Big Bang. It would be like a single ember igniting a new fire in an endless field of ash, a statistical inevitability in an eternity of waiting. Another possibility lies in the mysterious nature of dark energy. What if its repulsive force isn't constant but evolves over time? Some models propose that dark energy could weaken or even reverse its effect, allowing gravity to regain dominance. In this scenario, the universe's expansion would slow, halt, and eventually contract a big crunch that would compress all matter and energy back into a singularity, potentially sparking a new cycle of cosmic inflation. The heat death wouldn't be the end, just the prelude to a fiery reset. Even more radical is the notion that our universe might be part of an eternal cyclical model, where each phase of expansion and cooling is balanced by a subsequent collapse and rebirth. The conformal cyclic cosmology proposed by physicist Roger Penrose suggests that the infinitely stretched-out spacetime of a heat-dead universe could become mathematically equivalent to the high-energy singularity of a new Big Bang. In this mind-bending view, the universe doesn't so much rebound as it seamlessly transitions into a new iteration, with black hole collisions from the previous cycle imprinting faint patterns on the next. The common thread in all these theories is the universe's stubborn refusal to accept a true ending. Whether through quantum resurrection, dark energy's metamorphosis, or cosmic recycling on the grandest scale, the mechanisms might differ, but the underlying principle remains. Energy and information persist even in the bleakest epochs, waiting for the right conditions to begin anew. The heat death may seem like a finale, but in the unimaginable depths of time, it could just be the universe pausing to take a breath before writing its next chapter. What's truly humbling is realizing that these potential rebirths wouldn't happen on human timescales or even galactic ones. We're talking about processes spanning googolls of years, numbers so vast they dwarf every second since the Big Bang. Yet the mere possibility that the cosmos could find a way to reignite itself speaks to something profound. The universe appears hardwired for renewal, whether through the explosive death of stars, the mergers of galaxies, or just maybe, the patient workings of quantum physics in the dark eons after the last light has faded. So while heat death may be our universe's likely trajectory, its story might not end there. In the grandest perspective, even the void could be fertile ground. Cyclic cosmology turns the universe's story into an endless epic, where every ending births a new beginning. Imagine the cosmos as a phoenix collapsing in a fiery big crunch only to rise again in another Big Bang, over and over across eternity. This isn't just poetic imagery, it's a serious scientific model that challenges our understanding of time itself. At the heart of this idea lies a radical reimagining of cosmic fate. Instead of a one-way slide into heat death or eternal expansion, the universe might follow a rhythmic pulse of collapse and rebirth, each cycle lasting trillions of years but never truly ending. The mechanics of this cosmic reset are as fascinating as they are mind-bending. In some versions of the theory, when the universe contracts toward a big crunch, temperatures and densities soar to unimaginable levels. Matter and energy don't just squeeze into a singularity, they reach a state so extreme that the very laws of physics reboot. Quantum fluctuations, space-time geometry, even the fundamental constants might shuffle like a deck of cards, creating a new universe with slightly different rules. It's like hitting a cosmic refresh button, where each cycle gets a chance to play out differently while still carrying echoes of what came before. Roger Penrose's conformal cyclic cosmology takes this even further. He proposes that the infinitely stretched-out, heat-dead universe of the far future becomes mathematically identical to the high-energy singularity of a new Big Bang. In this view, the universe doesn't bounce so much as it seamlessly transforms, with black hole collisions from the previous cycle leaving faint imprints called Hawking points in the cosmic microwave background of the next. These ghostly signatures, if proven real, would be smoking gun evidence that our universe is just one link in an endless chain. What makes cyclic models so compelling is how they redefine recycling on the grandest scale. Every atom, every photon, every ripple in spacetime might get repurposed across cycles, not just within one universe. The carbon in your body could have been part of countless earlier universes, forged and reforged in an endless loop of cosmic alchemy. Even black holes, those seemingly final endpoints, might serve as cosmic archivists, their singularities preserving quantum information that gets rewritten into the fabric of the next cycle. Yet cyclic cosmology isn't without its challenges. The biggest hurdle lies in entropy, the universe's tendency toward disorder. If each cycle adds more entropy, how could the process continue indefinitely without winding down? Some theorists suggest that the extreme conditions of a big crunch might reset entropy, while others propose that dark energy's mysterious properties could hold the key. Whatever the answer, the very possibility of a cyclic universe reshapes our place in the cosmos. We're no longer just fleeting observers in a one-time universe, but potential participants in a saga without beginning or end. The implications ripple through philosophy as much as physics. If universes recycle, does consciousness somehow persist across cycles? Could the constants of nature evolve over eons, fine-tuning themselves for life with each iteration? While these questions venture beyond today's science, they underscore the theory's profound allure. Cyclic cosmology doesn't just offer a way to escape cosmic death. It suggests that renewal is woven into reality's deepest layers, a reminder that even the mightiest endings might just be preludes to something new. Imagine our universe as a sheet of paper floating in a vast, higher-dimensional space, a membrane, or Brane for short, vibrating with cosmic energy. Now picture another brane drifting through this unseen realm, its presence detectable only through mathematics. According to string theory, these branes could collide, unleashing enough energy to spark an entirely new Big Bang. This isn't just recycling on a cosmic scale, it's rebirth through dimensions beyond our perception, a process where the fabric of reality itself gets rewoven in the aftermath of a higher dimensional crash. The idea stems from the ekpyrotic universe model, which reimagines the Big Bang not as a singular origin point, but as the latest in an endless series of brane collisions. When two branes smack together in the bulk, the higher dimensional space they inhabit, the energy released doesn't just create stars and galaxies. It resets the entire cosmic clock, scattering matter and energy in patterns that might resemble our own universe but with subtle differences. Think of it like hitting the shuffle button on reality, where each collision remixes the fundamental constants: gravity's strength, the speed of light, even the number of dimensions that unfold into a habitable world. What's wild about this theory is how it solves cosmic mysteries while posing new ones: the near-perfect uniformity of the cosmic microwave background. That could be the smoothed-out aftermath of a brane collision, the universe's flat geometry, a natural consequence of two parallel branes merging. Even dark energy might be a lingering echo of the brane's gravitational pull as they drift apart after impact, stretching space itself in their wake. Yet the implications go deeper. If branes collide repeatedly, our universe might be one iteration in an infinite sequence, each with its own laws of physics. Some could be sterile voids, while others might teem with life variations on a theme written in the language of higher dimensions. The collisions themselves would be nothing like the apocalyptic crashes we imagine. In the bulk, branes might ripple toward one another in slow motion, their gravitational warps nudging them closer over eons. The actual moment of contact could be eerily silent from our three-dimensional perspective: no fireworks, no shockwaves, just a sudden infusion of energy rewriting the rules of space-time. Matter as we know it wouldn't survive the transition, but the quantum information underlying it might persist, repurposed into the next cycle's particles and forces. It's recycling stripped down to its most fundamental level, not just atoms being reused, but the very framework of existence getting a second act. Critics argue that brane cosmology pushes the limits of testability, but tantalizing clues might lurk in gravitational wave data or subtle anomalies in the cosmic microwave background. Some theorists suggest that ancient black holes could be scars from previous brane collisions, their peculiar spins hinting at trauma from a higher dimensional past. Others speculate that if our brane isn't perfectly flat, gravitational echoes from neighboring branes might one day be detected ghostly fingerprints of universes just out of reach. Whether or not the math holds up, the poetry of the idea is undeniable. It transforms cosmic recycling from a local process: stars dying, galaxies merging, into something boundless and multidimensional. The carbon in your cells, the light from your screen, even the space-time between us might carry echoes of collisions in a realm we'll never see. And when our universe's story ends, whether in heat, death, or contraction, it might just be setting the stage for another brane to brush against ours in the dark, igniting a new reality with the same primordial spark that started ours. The cycle wouldn't just continue, it would transcend dimensions, proving that even endings can be portals to worlds beyond our imagination. Vacuum decay sounds like science fiction, but it's a genuine possibility rooted in quantum physics, one where the universe could rewrite its own rules in an instant. Picture space as a vast, fragile bubble filled with energy, perfectly stable for now but secretly perched on a precarious ledge. According to quantum field theory, what we call empty space isn't truly empty. It's a seething quantum foam where particles flicker in and out of existence, governed by the laws of physics as we know them. But those laws might not be as permanent as they seem. Lurking beneath our familiar reality could be a lower energy state, a true vacuum waiting to be triggered. If a quantum fluctuation ever nudges a tiny region of space into this state, the consequences would be catastrophic and strangely beautiful. The moment a true vacuum bubble forms, it would expand at the speed of light, rewriting physics as it goes. Atoms, forces, even the very fabric of spacetime would be redefined within its wake. Stars, planets, and life itself would vanish without a trace, replaced by a new universe operating under entirely different rules. From our perspective, it would be an unfathomable end, but from a cosmic viewpoint, It might be the ultimate act of recycling. The energy released in this transition could spawn a fresh Big Bang, birthing a reality where gravity is stronger, light moves slower, or matter behaves in ways we can't even imagine. What's chilling is how easily this could happen. A single high-energy particle collision in some distant lab or a random quantum fluctuation in deep space might be enough to trigger the cascade. The universe wouldn't just end, it would upgrade itself, trading our familiar constants for something entirely new. Some theories even suggest this might have already happened elsewhere, with other universes succumbing to vacuum decay while new ones bloom in their place. If true, our cosmos could be just one iteration in an endless sequence of realities, each one emerging from the ruins of the last. Yet there's a twist. For all its destructive potential, vacuum decay might also be nature's most efficient reboot mechanism. Unlike the slow fade of heat death or the violent collapse of a big crunch, this process would be instantaneous, a clean break between one universe and the next. No lingering black holes, no stretched-out particles, just a swift transition into a new set of physical laws. The iron in your blood, the silicon in Earth's crust, even the photons from distant galaxies wouldn't be destroyed, they'd be transformed. Their underlying quantum information repurposed into whatever new structures the next universe permits. The irony is profound. The same quantum physics that allows particles to tunnel through barriers or exist in two places at once could also undo reality itself. But it's this fragility that makes our universe so remarkable. The fact that we exist at all suggests space has remained metastable for billions of years, teetering on the edge but never quite tipping over. Whether by luck or some deeper principle we don't yet understand, the cosmos has avoided this radical reset so far. While vacuum decay remains speculative, it forces us to confront a humbling truth. The universe isn't obligated to play by the rules we've grown accustomed to. At any moment, the ground beneath our feet, not just Earth but the very laws of physics, could prove as temporary as a sandcastle at high tide. Yet in that instability lies a strange kind of hope. If one universe can give rise to another, then endings aren't absolute. They're just the prelude to whatever comes next. Eternal inflation paints a picture of the cosmos far stranger than anything we've imagined, not just one universe expanding, but an endless sea of universes bubbling into existence, each with its own unique physics, its own history, and perhaps even its own forms of life. Think of it like a pot of water boiling eternally, where every bubble is an entire universe inflating into being, completely unaware of the others. In this scenario, the Big Bang wasn't a singular event, it's happening over and over, endlessly, in a process that has no beginning and no end. Our universe is just one bubble among countless others, adrift in an infinite froth of cosmic creation. What makes eternal inflation so fascinating is how it redefines recycling on the grandest possible scale. Instead of matter being reused within a single universe, entire universes themselves become part of an endless cycle. When inflation, the rapid expansion of space, ends in one region, it forms a bubble universe like ours where stars and galaxies can take shape. But elsewhere, inflation continues unchecked, spawning new bubbles eternally. Some of these baby universes might collapse instantly, while others could endure for trillions of years, each governed by slightly different laws of physics. The carbon in your body, the light from distant quasars, even the dark energy accelerating our expansion, they might all be local quirks of our particular bubble, with other universes operating under entirely different rules. The implications are staggering. In this eternal multiverse, every possible configuration of physics might exist somewhere. Universes where gravity is stronger, where time flows backward, or where matter never forms atoms at all. Most would be sterile, but a rare few, like ours, might strike the perfect balance for complexity, life, and consciousness. This isn't just recycling matter, it's recycling the very laws of nature, giving rise to infinite variations until something sticks. And when our universe grows cold and dark, the process will continue unabated, with new universes budding off in realms we'll never see. The mechanism behind this endless creation is as elegant as it is mind-bending. Inflation is driven by a peculiar state of space called a false vacuum, a high-energy condition that acts like cosmic fuel, stretching space faster than light. Normally, this process ends when the false vacuum decays, releasing its energy into particles and radiation, what we call the Big Bang. But in eternal inflation, some regions of space never stop inflating. They become exponential factories, endlessly spawning pockets where inflation does end, each one a separate universe with its own Big Bang. It's like a firework that never stops exploding, with each spark igniting new bursts in an infinite chain reaction. Critics argue this theory is untestable, but subtle clues might lurk in the cosmic microwave background, the afterglow of our own Big Bang. Strange patterns or anomalies in this ancient light could hint at collisions with other bubble universes in the distant past. Others suggest that advanced civilizations could one day simulate the conditions needed to trigger inflation, creating new universes in labs, though whether such a feat is possible remains pure speculation. What's undeniable is how eternal inflation transforms our understanding of existence. The universe isn't just expanding, it's proliferating, endlessly diversifying, ensuring that no possibility goes unexplored. And if inflation truly is eternal, then our cosmos is just one note in an infinite symphony, a fleeting moment in a cycle without beginning or end. The atoms in your hands, the screen before your eyes, they're not just stardust, but the products of a process so vast it makes galaxies look insignificant. In this view, recycling isn't just a feature of the universe, it's the engine of reality itself, endlessly rewriting the rules across an infinite tapestry of worlds. The universe could have been a much simpler place, just hydrogen and helium drifting endlessly through an empty void. No planets, no chemistry, no life. But against all odds, it chose complexity, forging heavier elements in stellar furnaces and scattering them across space so that one day, creatures like us could exist. This isn't just luck, it's a consequence of the anthropic principle, the idea that the universe's fundamental properties must allow for observers like us to arise. And at the heart of this cosmic fine-tuning lies recycling, the relentless process that turned the ashes of dead stars into the building blocks of life. Every atom in your body tells the story of this improbable journey. The oxygen you breathe was forged in the heart of a massive star that died billions of years before the sun ignited. The calcium in your bones was created in a supernova explosion so violent it briefly outshone an entire galaxy. Even the iron in your blood, the very element that carries oxygen through your veins, was once part of a star's core, squeezed together under unimaginable pressure before being scattered into space. Without the universe's recycling mechanisms, these elements would have remained locked away inside stellar graves, and Earth, along with every living thing on it, would never have formed. What's astonishing is how many steps had to align perfectly for us to be here. After those first heavy elements were forged, they had to escape their dying stars, mix with interstellar gas, and collapse into new solar systems. Planets then had to form in the right orbits with the right chemistry for life to emerge. It's a chain of events so delicate that if any link had failed, we wouldn't exist to ponder it. That's the anthropic principle in action. The universe isn't just random chaos. Its laws, its constants, even its recycling processes are precisely tuned to allow complexity to arise. This raises a profound question. Is our existence a fluke, or is the universe inherently built to produce life? Some scientists argue that in a multiverse where countless universes with different laws exist, we simply inhabit the one where conditions allowed life to evolve. Others see deeper significance, suggesting that the universe's ability to recycle matter and energy isn't just a quirk of physics, but a necessary feature for conscious observers to emerge. Either way, the fact remains we are here because the cosmos refuses to let anything go to waste. Think about that the next time you look at the night sky. Those stars aren't just distant lights, they're the engines of creation, tirelessly turning simplicity into complexity. Their deaths become the raw materials for planets, oceans, and living cells. The universe could have been barren, but instead it chose renewal, an endless cycle of creation and destruction that, against all odds, led to us. We are stardust, yes, but more than that, we are the universe's way of understanding itself, the product of cosmic processes so vast and ancient they defy comprehension. And that makes our existence not just probable, but inevitable, a whisper of consciousness in a cosmos that never stops reinventing itself. Trillions of years from now, the universe we know will be unrecognizable. The era of glittering galaxies and blazing stars will have long passed, leaving behind a cosmos transformed by time and entropy. Star formation, the engine that's been driving cosmic recycling since the beginning, will sputter to a halt as galaxies exhaust their last reserves of gas. The Milky Way, Andromeda, and all the other majestic spirals we see today will have merged and faded, their stars either burned out or flung into the void. Yet even in this twilight era, the universe won't be done recycling. It will simply shift gears, trading the fiery rebirths of supernova for slower, subtler processes that operate on timescales beyond human comprehension. Black holes will become the new custodians of cosmic renewal. In the absence of stars, these gravitational giants will dominate the landscape, slowly feeding on the wispy traces of gas and stray planets that remain. But they won't just consume, they'll transform. Through Hawking radiation, even the mightiest black holes will gradually evaporate, their immense mass dissolving into a faint drizzle of particles over eons. A supermassive black hole might take 10 to the 100 years to fade away, but when it finally vanishes in a flash of gamma rays, it won't be an ending, it'll be a homecoming. The energy and particles released will rejoin the universe's dwindling pool of resources, perhaps someday coalescing into new structures under physics we can't yet predict. Quantum mechanics might offer the universe's last hope for rebirth. In the unimaginable depths of time, even the vacuum of space isn't truly empty. Random fluctuations could, given enough time, spark new inflationary bubbles, birthing fresh universes with their own laws of physics. It's like shaking a cosmic snow globe. Trillions upon trillions of years from now, a tiny quantum event might trigger another Big Bang, resetting the clock in a region of space we'll never see. Our universe's story would continue not through stars and galaxies, but through the persistence of quantum potential, a whisper of order emerging from the chaos once more. The universe's final acts won't be dramatic explosions or collisions, but quiet, patient transformations. Protons, the building blocks of atoms, might decay over unfathomable timescales, breaking matter down into its most basic components. Dark energy's relentless expansion could stretch space so thin that even quantum bonds falter, dissolving the last remnants of structure. Yet even this heat death might not be the end. Some theories suggest that in a cosmos where time loses all meaning, quantum tunneling could eventually reassemble particles purely by chance, sparking a new cycle of creation from sheer statistical inevitability. What's humbling is realizing that this future isn't hypothetical, it's inevitable. Every star we see, every galaxy we admire is temporary, but the universe's genius lies in its ability to repurpose everything, even in the darkest, coldest eras. Black holes, quantum foam, even the fabric of space-time itself become participants in a recycling program that never truly stops, it just adapts. The story of the cosmos isn't a single narrative with a beginning, middle, and end. It's an anthology with each chapter written in the language of transformation, proving that even in the face of eternity, nothing is ever truly lost. It's only waiting for its next role in the universe's unending play. Humanity's existence is a fleeting spark in the cosmic timeline, yet we're woven into the universe's recycling story in ways we're only beginning to understand. Every breath we take is made possible by oxygen forged in ancient stars, every thought powered by atoms that have cycled through supernova and nebulae for billions of years. But our role isn't just passive, we've become active participants in this grand cycle. Through telescopes, we watch stars die and galaxies collide, piecing together the universe's recycling mechanisms. With particle colliders, we recreate conditions last seen moments after the Big Bang, unlocking secrets of how matter transforms. Even our spacecraft, like silent messengers, carry Earth's elements beyond our planet, tiny fragments of our world scattered into the cosmic void. Consider the Voyager probes, now drifting through interstellar space with golden records carrying humanity's story. Long after our sun becomes a white dwarf, these artifacts may endure not just as relics of a vanished civilization, but as evidence that the universe briefly produced beings capable of curiosity. In a sense, we've already begun seeding the cosmos with the products of our consciousness, however faint the signal. Future civilizations, or even alien species, might one day discover these traces, making humanity part of their own cosmic narrative. Our potential to shape cosmic recycling grows with our technological reach. Imagine a distant future where our descendants harness asteroids for raw materials, building structures that outlast stars themselves. Or consider the tantalizing possibility of stellar engineering, advanced civilizations redirecting supernova to enrich star-forming regions, or even triggering controlled nova events to redistribute elements. While this sounds like science fiction, the underlying principle aligns with the universe's natural tendencies, just accelerated by intelligence. We might one day transition from observers to stewards, guiding matter through its cycles with purpose rather than chance. The most profound legacy of humanity, however, may lie in the realm of information. Black holes famously erase information, but what if consciousness creates it? Our art, science, and stories encoded in light, etched into durable materials, or even imprinted on space-time itself, could persist long after our biology fades. In a universe destined for heat death, the preservation of information becomes a form of resistance against entropy. Some theorists suggest that advanced civilizations might ultimately upload their knowledge into the fabric of reality, using quantum fluctuations or space-time geometry as cosmic hard drives. If true, the universe's recycling program wouldn't just process matter, it could preserve the very essence of its observers. Yet for all our potential, we're also reminders of cosmic recycling's fragility. Life exists in a narrow window between stellar deaths and rebirths, dependent on elements that took generations of stars to produce. Our existence proves the universe can create meaning from chaos, but also how rare and precious such moments are. As the only known life forms capable of comprehending this grand cycle, we carry a unique responsibility to ensure the story doesn't end with us, whether through space exploration, scientific discovery, or simply sharing knowledge across generations, we keep the thread of consciousness alive, a thread that began in stardust and may one day weave itself into the universe's next great act. The cosmos doesn't need us to continue its cycles of destruction and renewal. Stars will explode, galaxies will merge, and quantum fluctuations may birth new universes regardless of whether we're here to witness it. But our presence adds something extraordinary, a moment where the universe became aware of itself, looked back through time, and began deciphering its own origins. In that act of understanding, we've already altered the cosmic story. The question isn't just what role we'll play in future recycling, it's whether the universe, having briefly awakened through us, will ever be the same. From the fiery furnaces of newborn stars to the silent evaporation of the last black holes, the universe operates on a principle of perfect efficiency. Nothing is wasted, only transformed. Every supernova explosion scattering heavy elements across the void, every galactic collision triggering new waves of star birth, even the quantum flickers in empty space hint at a cosmos that thrives on renewal. We're not just observers of this grand cycle, we're products of it, our very atoms bearing the fingerprints of stellar ancestors that died billions of years before Earth formed. Yet for all we've uncovered, the universe still guards its deepest secrets. Does dark energy's acceleration have a limit, or will it stretch space-time into infinite silence? Could quantum fluctuations in a distant future spark an entirely new cosmic dawn? The answers may lie beyond our current grasp, but the questions themselves reveal something profound. Our desire to understand the universe mirrors its own relentless creativity. Just as galaxies recycle stardust into planets, we transform curiosity into knowledge, building bridges across time and space. The night sky is more than a static tapestry of light. It's a living chronicle of destruction and rebirth. When you trace the arc of the Milky Way or spot the faint glow of the Andromeda galaxy, you're seeing a snapshot of a story that began nearly 14 billion years ago and will continue for trillions more. Those distant points of light aren't just relics, they're promises, proof that the universe knows how to reinvent itself against all odds. So what comes next in this cosmic saga? Will dark energy rewrite the rules, or will gravity stage a comeback? Could civilizations of the far future learn to harness these cycles, turning cosmic recycling into an art form? The possibilities stretch as far as the imagination, limited only by the laws of physics, and even those might be more flexible than we think. One thing's certain, the universe isn't done surprising us. As we wrap up this journey, remember you're not just part of the universe, you're a conscious expression of its endless recycling, a way for the cosmos to reflect on itself. So the next time you feel small under a starry sky, think bigger, you're stardust that learned to wonder, and that might be the universe's greatest trick of all. Now it's your turn. What do you believe lies ahead in this infinite cycle? Drop your thoughts below, and if you've enjoyed unraveling these cosmic mysteries with us, hit subscribe to explore more of space's deepest wonders together. The universe's story is far from over, and neither